So welcome back. This video we're going to continue talking about interpolation. We'll first review a little bit what we did in the last video, and then we'll find a more general way to write what we did in the last video, so that in this more general way it'll be easy for us to investigate other methods of interpolation, in particular spline interpolation. So in our last video we saw that if we're given some data points, and we wrote this data points as a function of x, but with x limited to integer samples, right? So we have x measurements only at some specific grid, which in this case we chose for convenience to be the integer grid. So this data is given. We're going to seek a model. In this case, our model was a polynomial equation, which has certain coefficients. And we're going to seek a model that passes exactly through this to the given data, right? So at the given points, like the given grid or nodes, the model should be equal exactly to the data. In between the points, of course, the model will do something, and we don't know a priori, without extra information, we don't know whether the model is right or wrong there. But nonetheless, it is a model, and we're allowed to then interpolate, produce a value at any point of x we would like, because now this model allows for us to evaluate this, right? So if, for example, if we wanted to evaluate what the function is doing at the grid point of 1.5, right, we can, because now we can plug in 1.5 here, whereas before, with just given the data, we only had the values here, 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 here. So long story short, if we found that if we take this as our model and then rewrite this requirement that the model should be equal to the given data at the samples where the data is given. So we say, okay, for sample 1, we write out this equation. For sample 2, we write out this equation. Sample 3, and so on. We write out this equation. My apologies, this should have been a 3 here, so let's fix that. Right, we saw that if we did this, then we can write this entire system of n equations and n unknowns as our old linear system that we just learned about in the previous videos, where we have the matrix of coefficients 8, the matrix of values of our system is given as A, C is a vector of unknown coefficients, and F is a vector for our data. And the conclusions are that for this linear system to have a unique solution, we need to have n equations and n unknowns. If that is satisfied, we will have the solution. So what we're going to do today is go a step beyond and find out a more general way of writing this. Right, and the basic notion is we'll start with our model, which in this case before was, our model was v of x will be equal to sum over p equals 1 through n of some coefficients p. How do we find these coefficients? We solve for this linear system using Gaussian elimination or some other method we would like to solve with, times our polynomial here, right? So in this case, this would be n minus p. Or, my apologies, I think we wrote something different here, so I'll keep the same as before. It should be pretty much the same. I mean, the order is inverted, right? So it should be p minus 1. So here we have it. And we would like now to just rewrite this in a slightly different way. I'm going to make the following this substitution. I'm going to call this guy here something else. I'll call it phi as a function of x with some subscript p. Right? It's just calling it something else. There's nothing more going on here. Right? So we can write this now as v of x equals sum p equals 1 through n c p phi p of x. And the beauty about doing this is that now we can take this definition and plug in other definitions here. That is, instead of a polynomial, we can choose something else, or some other form, or some other function. Right? Again, our previous choice was this particular polynomial, but it's not the only one that we can use to make. Here's another one, and this is where we start into the topic of splines. Let's look at a very basic example for what a spline is. Let's define a function we'll call phi like this, where this function will be 1 minus the absolute value of x when x is less than or equal to 1, and it will be 0 otherwise. So what does this mean? Let's plot this function. So we have here we have an axis here, and let's plot, let's say this is a we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So let's say that over here we have 1 in the x-axis, and over here we have -1, and of course by definition then here this is going to be 0.1, 0.2, 0.3, and so on. So this is our x-axis. So now we're plotting this equation, right, this function, and the plot for this function, let's say again that let's say this value here is 1. This function will be plotted as a straight line between here and here, and the straight line between here and here. And of course it extends beyond this, but it will be 0 beyond this guy. Oops, this should have been lined up exactly with 0, but for some reason it didn't. Right, so this is our definition, right? So now let's take a look and see what happens to this function if we write it slightly different way. So here's our function again, and instead of doing this, we're going to ask, what does this function here look like? So let's plot it. So let's copy, paste. We're going to have to now extend our axis beyond this, right? Because we have a bigger axis, so oopsie. right? And again, before we had here to be -1, and this was 1. So roughly speaking, we're going to have here 2. And let's say, roughly speaking, here 3. And as actually we mentioned this before in one of the first videos in this class, when we are shifting this function by 1 here, it's like we're moving this entire function here one step to the right. So we're going to, I will use a different color here and plot this function now this way. Right? And you can see that this function here was our phi of x, and this one here is the plot of phi of x minus 1. Like, we can do one more just to drive the point home. Right? Let's plot the following one here. And this plot here will be phi of x minus 2, right? And so on. We can shift this function to the right by adding a negative value here, or we can also shift it to the left by, this would turn into a plus. In any case, we can write many of these functions, and then we can ask, what does the sum of them look like? For example, if I sum 1 times these functions, x minus p, and let's say from p equals, let's say 0 and up to 2, right? So that means we're summing this red function here with this green function with this blue function. The end result will be what I'll be plotting here in orange. Right? This will be the plot between, let's say, 0 and 2. Right? So this plot here. And of course, it came out to be exactly that because I chose the coefficient here to be 1. Of course, I could have multiplied any of these by some other coefficient, in which case it would not have been given me the constant function between 0 and 2, but given something else. So the general way to write this function here is, let's say, p equals 0, let's say, to n minus 1, right? We're still, by doing this, we're still summing over n terms, right? I just shifted the coefficients, and there will be some general coefficients here, c of p, and the variable phi minus p. Right? So this gives us a way to essentially write piecewise constant functions. And we can repeat the interpolation procedure that we just described for polynomials for splines of this form. In this case, it is called b-splines, and this particular example is the hat function, or b-spline of degree 1. And there are many other examples like this. They can have more smoothness and so on. But the general strategy is to do the same exact thing. So if we go back to our equation here before, right? So we wrote this now more generally, and all we have to do is now plug in this new function definition in here. So what we're going to do is call, in our case, phi of p of x to be equal to this other phi x minus p and minus 1 in our case, because we shifted the index to sum from 0 to n minus 1 here, so we have to start from the same definition, right? But basically, using this new definition here, we can plug this back into our model and redevelop our linear system, right? And however, rather than these numbers here, you will have something else. You will have, let's write what this new things here would have been, right? So this is going to be phi of p evaluated at 1, right? Here you would have phi, oh, sorry, in this case p equals 0, right? So let me write that in this case. Let me erase this. This is going to be phi 0 of 1. This is going to be phi 0 of 2, and so on, right? Phi 0 of 3, and so on. On this guy, you have phi 1 of 1, phi 2 of 2. I'm sorry, not phi 2 of 2, phi 1 of 2. And here you have phi 1 of 3, and so on, all the way to the end here, where you have phi n minus 1 of 1, phi n minus 1 of 2, and so on. Right? So if we make these substitutions for these values, we don't even have to rewrite the whole thing, right? So here, this would be substituted according to this thing above, and we would end up with the same linear system as we have before. And this is how we do spline interpolation. We seek a new definition for this phi function here, and we simply plug it in to our model given over here, right? This is our original model, and all we do here is plug in phi, in this case p minus 1 of x. And there you go. Now you have a more general mechanism to interpolate data using a variety of functions, and all you have to do is come up with good examples for phi. That should be, we saw 2 examples. We saw polynomials, and we saw this spline examples, specifically saw the spline of, it's called a hat function, right? This is the plot here. It's called a hat function. There are many other examples, some of which you might see in signal processing, image processing, and PDEs, and so on, which we may get to later on in the course.